Hello, everyone. Today, we're presenting our project, which is a vision for natural disaster recovery through automated damage assessment and relief prioritization using satellite images. My name is David, and I'm presenting with Chris and Kirk. Our work focuses on how satellite images paired with machine learning can help emergency responders rapidly understand the scale of the damage after major disasters like wildfires, flood, and hurricanes. By automating this process, we can help reduce response time, improve resource allocation, and ultimately support communities when they need it most. Can you go to next slide? Yeah, this is an overview of the topics we'll cover today in this presentation. Can you go to next slide? Yeah, satellite images are important in disaster responses because they provide large scale real-time visibility when the access is limited on the ground. Our objective in this project is to use engineered features, which we had 12 in this case, from these satellite images to automatically classify disasters and estimate the damage level. We focus on two tasks here, task A and task B. Task A distinguishes between Midwest flooding and Southern California wildfire, and task B predicts damage levels from 0 to 3 for Hurricane Matthew. So together, these tasks highlight how machine learning can support disaster relief. Okay, next slide. This slide summarizes the two prediction tasks in our project. Task A is a binary classification problem where the goal is to distinguish between two very different types of disasters, Midwest flooding and Southern California wildfire. These events leave distinct signatures in the satellite images, so the model learns to separate them based on texture, color, and environmental patterns. In Task B is a more challenging task. It's a multi-class problem where we classify Hurricane Matthew images into four damage levels, ranging from no damage to fully destroyed as we move from level 0 all the way to level 3. The patterns become increasingly severe and harder to distinguish. So these tasks together allow us to test how well machine learning can support both disaster identification and detailed damage assessment. Next slide. In our EDA analysis, we focused on understanding what visual signals differentiate disasters in satellite images. We examined RGB color distribution, texture patterns, and frequency-based features to see how flooding, fires, and hurricane damage manifest differently. The key challenge here was finding features whose distributions are separable. For example, features that clearly distinguish fire from flood in task A, or separate minor damage from major damage in task B. Next.
Thank you, David. So to begin our EDA, we started simply by looking into a sampling of the images available for each class in each task. And on the upper left, we see two examples for the Midwest flood and Southern California fire images. And on the lower left, we see two examples for each of the Hurricane Matthew damage levels. And this initial look helped us to identify three properties of the data set that we found to be important to our goals. One is that there's black padding in nearly 20% of the images, which we removed before feature engineering. Second is that there's a class imbalance clearly across the damage levels in task B, whereas there's no class imbalance across the images available for task A. And we also saw, third, that there are clearly color and texture edge patterns that, when quantified through feature engineering, might offer class discriminations that a machine learning model could learn. So we proceeded then to feature exploration and selection, focusing on descriptive statistics for color and texture across each image and comparing the distribution of those statistics between classes. We settled on a few metrics that represent mean and variance in color channels, RGB, and mean and variance in local patterns, microtextures, directional or oriented textures, and edges. So this is specifically, we're interested in the RGB color channels. Local patterns is defined by linear binary patterns, which you might think of as terrain irregularity, or directional textures as defined by the Gabor filter, which might be thought of as roads, fields, coastlines, and edges as defined by a Sobel filter, which might be thought of as structural outlines or abrupt changes in contrast associated with disordered debris. And just to highlight a few of the distinctions between the classes in task A, we see here that fire images tend to have a higher red mean and blue mean, consistent with a warmer tone or exposed burn surfaces in the case of red, or smoke, haze, and ash in the case of blue. Flood images tend to have a higher LBP mean and standard deviation, consistent with higher local texture and heterogeneity, which might be explained by degrees of disordered terrain and debris. For task B, we found that texture features are primary key class separators. And we'd just like to highlight a few of these. For example, the RGB means vary slightly across the damage levels, while the red standard deviation and the blue standard deviations change, one trending down and one trending higher at intermediate levels. And as we said, the texture features are the most relevant here, where the LBP standard deviation in particular and the mean appear to rise with damage. The Gabor mean trends downward, and the Sobel mean and standard deviation trend upward. All of these consistent with increased disarray and debris as the degree of damage increases. And finally, we did perform pairwise correlation analyses on these features, suggesting that subsets offer complementary or distinct information within each class, and they offer distinct separation between the classes. So this may offer a machine learning model sufficient signal to distinguish between the individual classes in task A and the multiple classes in task B. So we proceeded with the 12 features to explore their capacity to inform learning by 3 models. The first model was a naive Gaussian Bayes model with or without principal component analysis. And we really considered this just a very simple baseline model. Distinctive about NGB is that it assumes each feature follows a normal distribution and that the features are uncorrelated.
For the second model, we explored logistic regression. This model is a classifier that draws a linear boundary using our 12 featured, 12 engineered features, like RGB values, texture measures, and Gabor responses. We use this model to separate flood from fire in task A, or the 4 hurricane damage levels in task B. It performed better than naive Bayes because it can capture more structures in spectral and texture features. However, its limitations showed up in multi-class problems.
Finally, we explored an artificial neural network, or ANN for short. An ANN is a nonlinear model that should, in theory, better learn interactions across RGB, texture, and edge features. It consistently performed best on both of the tasks and handled nonlinearity and class imbalance better than the simpler models. Naive Gaussian Bayes performed moderately well on task A, with the addition of PCA to this model providing a moderate improvement in accuracy. However, this accuracy was eclipsed by the logistic regression and advanced neural network models that both reached the upper 90s for task A. Due to this clear difference in performance, we chose to focus our efforts for task B solely on the logistic regression and ANN models. For task B, logistic regression achieved an F1 score of 0.46, indicating that while the model did learn some helpful structures regarding color and texture features to separate the Hurricane Matthew damage labels, it struggled with the dataset class imbalance and its constraint to model a linear separation between classes with likely nonlinear classification boundaries. The ANN, on the other hand, seemed to better handle the nonlinearity of the engineered features and the class imbalance found within task B, as compared to the logistic regression model, achieving an average F1 score of 0.57 across its 5-fold cross-validation. With the ANN outperforming the naive Gaussian Bayes and logistic regression models, we wanted to specifically highlight its structure in this presentation. RANN was the most flexible model, able to learn nonlinear patterns across both the spectral and textural features. It performed best on these tasks because it was able to capture interactions that simpler models such as naive Bayes and logistic regressions could not. The architecture we used for the ANN included an input mirrored features from our EDA with one hidden layer and a learning rate of 0.01 for stochastic gradient descent. For task A, we utilized 64 neurons and 3,000 epochs. As for task B, we used 20 neurons but 10,000 epochs. Class weights for task B were also introduced due to the unbalanced nature of the dataset. The ANN performed better than other models as it was able to learn from the nonlinear boundaries between the features and is better suited for multi-classification problems. This ultimately led it to have the best performance out of the investigated models. The ANN's performance is highlighted in the confusion matrices for both task A and B. From the confusion matrix for task A, one can see the ANN model correctly identified all Midwest flooding images while only misclassifying 2 images of the SoCal fire. This is reflected in the high accuracy score for the model and emphasizes the model's ability to easily distinguish the 2 disaster types based on our selected features. However, for task B, there is much more frequent misclassification across the damage levels. The overrepresented classes of 1 and 3 had the highest proportion of correct classifications as compared to the underrepresented classes of 0 and 2. As expected, the model misclassifies these underrepresented classes a majority of the time to its nearest neighbor, as damage level 0 is often predicted as damage level 1, while damage level 2 is also predicted as damage level 1. Overall, however, the model identifies damage levels 1 and 3 with high reliability, contributing to the overall weighted F1 score of 0.57. Evaluating our model results from task A and task B, we conclude that our primary goals were accomplished. From the given training images, we were first able to clean the images to remove any unnecessary noise such as the black padding. We were then able to engineer 12 unique features, both spectral and textural, from these images and demonstrated that they could separate the necessary classes during our EDA. These features were fed into 4 classification models, training each model on the curated features and confirming their output predictions via accuracy and F1 score. Finally, having determined that the best performing model was the ANN, we utilized the trained model to make predictions on the unseen images within the test dataset, resulting in an accuracy for task A of 99.4% and an F1 score for task B of 0.51. Thus, the workflow that spanned from an initial image to ultimately a class prediction is concluded. Thank you for your time.